want to jump right in and talk about a little bit about ourselves. So we are co-maintainers of the rustls TLS stack within Rust. We pronounce it rustls. Sometimes people also find different pronunciations. It's 10 years old this year. It's been quite popular, so we're getting like 50 million monthly downloads today. So that's nice, and we're hoping to release 1.0 this year, but we are talking today about a different project, which is somewhat related, which is called uPKI. And I wanted to dive right in with the problem, which is that if you are not in a browser, but you are on a Windows machine, then if you use curl to get or to make a connection to a system that has a revoked certificate using a TLS connection, then it fails. But if you do the same on Linux today, then it just works. And that's not good, because while you might like it, your command's working, if the security is not guaranteed because the certificate was misissued, or there's another problem with it, then you would prefer your connection to break, like on Windows. So this has been a long-standing problem, sort of falling outside, I guess, the scope of anyone feeling responsible for it. And we, as a TLS stack maintenance group, have some thoughts about how to solve this. And so earlier in this year, there was an article in the LWN, great magazine. Everyone should subscribe. And after that happened, I thought, well, let's see if we can find some support for solving this problem. And so I reached out to John at Canonical, because he had done some cool projects with sudo rs and uutils. And so figured out, hey, can we work together with Canonical to solve this problem going forward for Linux and any other operating systems that might not have a system verification solution. So a little bit of background, because there might be, not everyone might be as familiar with TLS as we are. So TLS is the protocol dominating sort of use of secure connections on the internet. It used to be known as SSL until about many years ago, I think 20, 25 years ago now, when it was renamed to TLS. And its notion of security hinges on sort of three things that cryptographers distinguish, which is confidentiality, which is maybe the more conventional sort of, I send you something and you can read it, but other people cannot. But that's not enough, because if I send you something and other people cannot read it, but you don't know who's actually on this other side who can read it, then it's sort of meaningless. And then there's also integrity so if I send something to someone else, but an attacker can modify the message that I sent, and without the other side noticing, then it's still not really working as a secure message channel. And so uPKI works at the level of certificates, and certificates are mostly concerned about the second part, the authentication. So am I talking to the party that I want to be talking to? And so how that works in PKIs, so that's public key infrastructure, and the largest public key infrastructure is sometimes called the webPKI. So that governs browsers and TLS certificates issued by certificate authorities like Let's Encrypt. And the way it works is that you configure in your system or in your application trust anchors or certificate authorities that you want to trust to issue certificates. And then they maybe transitively issue a certificate for the party that you're talking to. And that's usually, you usually recognize them by a domain name. And so the certificate authorities recognize or validate that the domain name belongs to the owner of a private key. And then if you are presented with a certificate and you can challenge the owner of the certificate with a public asymmetric crypto, and so you can check that they have the private key belonging with that certificate. And so you authenticate their use. Certificates are time limited, which is important. Sometimes, so it will be time limited. Until recently, certificates were allowed to be up to a 400 days lifetime. That's going down slowly because browsers and other folks governing the webPKI are trying to reduce trust in the system, so that if you issue new certificates more often, then if a certificate is bad or there's some issue with the private key leaking, then the certificate will not be used in bad ways, because or it will be usable short term. And so there's an additional system to be able to revoke a certificate, to say, to have a certificate authority say, there was a problem with this certificate, you should no longer trust this certificate. And that's called certificate revocation. And so certificate authorities are obliged to publish a certificate revocation list for any certificates that they published or issued that should no longer be trusted. And so earlier in the slides before, you were seeing a certificate that was supposed to be revoked, but is not actually recognized as revoked by the local curl. And then there's certificate transparency, which is a separate system in the uPKI, which is used to sort of collect all the certificates being issued by the public uPKI certificate authorities, which helps because now there's a lot of people that can monitor issuance and see if there's any issues with misissued certificates and stuff like that. That's a bit of introduction about TLS. Let's move on to more of the specifics of how uPKI works. So Mozilla obviously has this problem for Firefox, and browsers have solved this problem. Like even on Linux, you won't generally see revoke, or you will generally see an issue or an error in your browser if you go to a website with a revoked certificate. And so Mozilla built a solution for this in 2020, where they have a way to efficiently collect from the certificate transparency logs all the certificates that have been issued, and then they managed to make a very compact representation for that. It's a bit like a Bloom filter, but I think they've iterated a bit on the exact data structure they used. There was a nice white paper about it, and now you can have like a pretty compact way of both downloading that data when you have to get a full set, and then also doing like deltas over time, so that you don't have to re-download the whole set over time, or every day, every time when you want to get a fresh set. And an added benefit of this is privacy. So before, you used other ways to check for revocation, like OCSP, but that means every time you want to check if a certificate has been revoked, you put out a call to the certificate authority, which is recognizable and sort of leaks that you are looking at this website or want to look at this website. Whereas with this system, you download the whole bundle, and you can, in an offline way, without leaking any traffic analysis, you can see whether it's revoked. And so basically, the core idea of uPKI is just packaging this CR-Lite system for use outside the browser by any libraries or applications on any system, pretty much. Yeah, and so I asked Mozilla about this, and they told me a few months ago that in common usage, they see about 50,000 unique clients running into a revoked certificate per day, and that means that there are quite a lot of blocked connection, like on the order of a few million blocked connections. That would be that today outside of the browser are just happening, but are not being blocked by the certificate being revoked. And so here is a bit of a diagram of what we are trying to build here. So you have the Mozilla servers that have these CR-Lite filters. That's their data structure in a bunch of files. So they append new files over time so that you can download these deltas. And then for uPKI, we've built a mirroring tool so that Canonical or other parties that are interested in this stuff can run their own mirror for the filters. And then we have the uPKI fetch CLI interface, which will download the data fresh, the latest data to your local machine, and then over time can fetch these deltas instead of getting a fresh set. And so you would typically put this on like a systemd timer or some cron job to make sure that you always have a recent set of data with all the latest revocations. And then we have built a bunch of libraries and tooling around this so that you can simply query this local data. So that's a Rust library that people can use, which is sort of at the core of all the other things. And this is something that we have packaged a very early version of today, so you can try that out. And then there's a CLI way of calling into that, so you can test. Basically, if you give it a domain name, it will say, hey, is this certificate revoked or not? And then we have some CFFI dynamic libraries. So like all these other systems that are working at a C layer or systems that use a CFFI can call into our uPKI infrastructure and use the local set by referencing some configuration or pick the global system-wide configuration. And we then have another wrapper specifically for OpenSSL, because OpenSSL doesn't have a way of dealing with this by default, but it does have a callback interface. So when you have verified the certificate, you can give it a callback and say, with this callback, you can do additional verifications to determine whether it should be verified. So we have built a way to call to just a simple one-line change, basically, to pass a callback into OpenSSL to make use of this uPKI stuff. And then for the Rust ecosystem, we have a crate which makes it really easy to integrate all of this with our rustls TLS stack, so that our rustls verifier can sort of opt into this and be protected by default in all the Rust applications.
Cool. So just running through what we've done so far, which is kind of reiterating that last slide. But yeah, all these things exist at the minute. The last one is something I'll go through now. So it's not a live demo. I didn't want to offend the gods. But it is a quite nice little patch. I would say that, like, this is the minimal patch. The actual patch is quite a bit bigger because it's going to be an optional dependency of curl. And it also comes with like 400 lines of autoconf because that is the zen of autoconf. But yeah, as you can see, it fits quite nicely into an average caller of OpenSSL, which I would describe curl as. So you're going to find a lot of typical use of OpenSSL which look like this and are amenable to be integrated like this. And this is the result. So the top thing is what we saw on the first slides, and the second is what you get as the result, which is it's not a new error message, it's just triggering a new error case. So OpenSSL already supports the idea of certificate revocation in itself, so it has existing errors that you can just raise, and this is what those look like when it happens from curl, which is quite nice, quite rewarding to make a effectively single line change and get something that works. So the other thing I want to say before I go on to this slide is there are some more things to integrate to. So I think the eventual goal is to have this really well integrated across a whole set of different applications. And not everything uses curl. There's quite a lot of things. You know, if your application like calls a load of webhooks, then you might use libcurl underneath, and that last patch will work for you really well. But you might have other things that use GNU-TLS, or you know, a whole variety of the platforms that you might write your application in. Maybe you write in Go. So we've got some other demos like demonstrating how you would call into this through the CFFI from Go. And so yeah, the whole idea is just to make it quite low friction to opt into this and then spread it and have a good level of adherence to certificate verification working well. But the other ideas we have about uPKI and what it can address, these are all, I would describe them as quite low assurance ideas. And what I mean by that is they're not changing trust decisions in a way which make new connections possible. So we're not, starting to synchronize maintain a new trust store. That would be a high assurance thing where you'd want really like good levels of cryptographic assurance and transparency. These are all about taking things which work today and layering on top of that additional restrictions. And those are restrictions which are like coming in the future and are common in browsers today. So the first one is intermediate preloading, and I'll talk about certificate transparency enforcement, which is again another thing which doesn't happen generally outside browsers. And then we'll talk about Merkle tree certificates, which is still in the future, but it's coming. And yeah. So intermediate preloading is basically it's not a great situation. There are a lot of servers which are misconfigured, but they're misconfigured in a way which browsers deal with, and largely other HTTPS and TLS clients don't deal with. And there's this idea of, it's called AIA fetching. So you basically look in the certificate that you got from the server, which gives you some list of URLs that you can go and download the rest of the certificate chain from. And if you do that, obviously you've now leaked over usually plain text HTTP that you were going to this server, which is something that we like to avoid. It's also got over this terrible architectural layering problem where now your TLS library is making HTTP calls, which tends to not happen. So browsers either do that, which is not a good idea generally, or Mozilla basically just bundle up the entire set of intermediates that could possibly be used in a publicly trusted cert. And yeah, we can do the same. So we are just going to reuse the synchronization component we made, and we will populate a directory of all the possible intermediates certs, and then you can just give that path to OpenSSL or your certificate verifier of choice. And basically every certificate verifier already has this as a concept that these are a bunch of other certificates. They're not trusted certificates, but they can be used to form a path from the certificate I've got to a trusted certificate. So that should work pretty well. And again, it should be really easy to integrate into applications. But yeah, you need to keep them up to date. They don't change a lot, maybe like a few a week. So yeah. And then certificate transparency. So one thing that often happens is that a certificate authority messes up. And they mess up in a public way. It's always in a public way. And browsers and the root programmers go, this is not so good, so we are going to distrust you. And the way they express that distrust is they say, after this date, we will not trust a certificate issued by you. And that date is established through certificate transparency. But if you're not verifying certificate transparency, then you cannot enforce that extra constraint. So generally, people don't, outside browsers again. And what you tend to find is that those roots just stick around, and they are continued to be trusted for months, years after everyone else has distrusted them. Big call out to the CA certificates package on Debian, which is establishes this as like a so we can do a bit better than that, and this is a way of doing that. And again, this is taking a connection which does work today, probably shouldn't work, but we have the technology, we can make it not work in the proper way. The other thing I want to touch on is Merkle tree certificates. So this is a new thing. This is supporting post-quantum crypto, which tends to be quite hefty, and will make certificates, specifically public keys and signatures, really, really big in certificates, and that will be a challenge for actually getting widespread adoption. It makes them so big that like now your TLS connection will take a lot more data. So this is an interesting new effort to basically combine certificate issuance with certificate transparency and have a single sort of truth source in a certificate transparency type log. One of the things you can do there is you can kind of get a proof that a certificate was included in that log, and instead of all the public keys and signatures, you can just publish these things. They're called landmarks, and if you have an up-to-date enough landmark, then your TLS server can go, I know that you have all this information, and if the information is properly up to date, then it can just include this small proof. So it elides all the big certificates and public keys, and your TLS connection is possibly even smaller than it is today, which would be amazing. But again, it's something that you need to synchronize regularly. So uPKI is well placed to solve that problem as well. And obviously, this is going to be another thing where browsers will and are taking the lead in deploying this, and things like your application server, which might call a load of webhooks or whatever it is, will lag unless someone comes along and does the work. So yeah, to reiterate where we are, there is a couple of mirrors of that data, one maintained by Canonical, which is cool. We've got this synchronization tool that you can run from a systemd timer or cron or whatever you like. The tool is designed to either run at a system level, so in a multi-user thing, or you can run it per user and just have your own little cache. So it's quite flexible in that regard, mainly because we didn't want to make the decision for someone else, so you can package it in both ways. We do have a bit of packaging work to do. We've done all those integrations, got some demos and stuff on the README of the repo, and yeah, we expect to have it in Ubuntu soon. Cool. So there's the repo. Please go try it out, and yeah.